Mr. McFall presents Science You Can Do in Your Home. Please be advised, Mr. McFall is a trained professional. Make sure you follow all safety precautions before attempting the experiment shown in this video.
Welcome to another science experiment you can do at home. For this science experiment, you're going to need some distilled vinegar, some bicarbonate of soda, some tea lights and something to light them with, a large bowl, a measuring jug, a smaller glass, and then something to hold the vinegar while you pour it in. And finally, something which fits over the top of your measuring jug. I'm going to be using this plate. Okay, so to begin with, I'm going to take my large bowl and I'm just going to light my tea light. Now, what you're going to do is you're going to measure out about 5 grams of sodium bicarbonate into the glass. You're going to place that glass into your measuring jug. Then you're going to measure out about 60 mils of your distilled vinegar into a bottle. And it's really important that you don't add this all at once, because if you add it all at once, it's going to overflow your smaller glass on the inside. So we're going to add it a bit at a time. We're going to trap the gas in there by every time we add it, we're simply going to put that plate on top to stop the gas from getting a small amount of the vinegar to begin with. You can see it fizzing up, and I've put my plate on top to trap any gas. Once that fizz dies down, we can gently lift up our plate, pour in a little bit more. Again, just being careful that it doesn't overflow that inside glass. Waiting for the fizz to die down. Add in a little bit more. And then we can add our final amount. Okay, now that has fully reacted, this is now filled with a gas called carbon dioxide. Carbon dioxide is more dense than air, so it should stay inside this vessel whenever we take out this cup. And now we're going to take that very quickly and pour it into the bowl. And you can see that the carbon dioxide has extinguished our tea lights. So I thought I'd take this opportunity to explain the concept of moles in chemistry. If you asked a biologist what is a mole, they might tell you that a mole is a small burrowing mammal with dark velvety fur, a long muzzle and very small eyes. But if you were to ask a chemist what a mole is, they have a very different answer. Mole is actually the first part of the word molecule. And the term mole was first coined by a German guy called Wilhelm Ostwald, although he probably would have said Molekül with an umlaut over the U. The reason we use moles is because molecules and atoms indeed are ridiculously small, and so having to keep track of them in experiments can be quite difficult because there's so many of them. And so we use the concept of moles as just a big number as a way of keeping track of them. Here is an example of just how small a mole is. We're starting off here with times 12 font, which is just regular typewritten font. And we're zooming in past a grain of salt, past an amoeba, a paramecium, a human egg cell, past a red blood cell, an X chromosome, and we're still not down to the molecular level yet. There's a mitochondria, the powerhouse of the cell. There's the rhinovirus, the cold. There's an antibody, some transfer RNA. So we're getting down to molecule size now. There's a glucose molecule, a water molecule, and finally a single carbon atom. So things get quite small at the molecular and atomic level. If I was to ask you what a pear represents, you'd probably tell me 2. If I was to ask you what a dozen is, you know that's 12. If I was to ask you, say to you, you owe me a score, you know that you owe me £20. But what's a mole? Well, a mole to chemists is just a very big number. In fact, it is 6.02 times 10 to the 23. That number written out in full looks like this. So it's a pretty big number. In fact, if you had a mole of marbles, it would cover the surface of the earth to a depth of 50 miles. So actually, I worked this out. Here is Mount Everest, and Mount Everest has an elevation of 5.498 miles above sea level. So if we were to have a mole of marbles, this is what it would look like in comparison to Mount Everest across the entire surface of the earth. So that should give you an idea of the kind of big numbers that we're dealing with. So the next question is, if we have so many of these molecules, how much does a mole weigh? Well, a mole of carbon weighs just 12 grams. It's hard to believe, but in that tiny pile, there is 6.02 times 10 to the 23 molecules of carbon. Now you might ask yourself, well, where did I get that 12 grams from? Where does that come from? It comes from the periodic table. And these numbers right up here, that's the relative atomic mass. And that tells us how much 1 mole of that element weighs. So what does this have to do with the experiment that I just showed you? Well, let's take a look at the vinegar. Vinegar is ethanoic acid. It has the compound formula CH3COOH. So how much does 1 mole of ethanoic acid weigh? Well, let's take a look. We first draw out a little table like this. How many carbon atoms do we have? We have 2. Carbon weighs 12 grams per mole. We have 2 of them, so that's 24 grams. Hydrogen, we have 4 of them in this compound. So hydrogen weighs 1 gram per mole, so that's 4 altogether. Oxygen, we have 2 here, and it weighs 16 grams per mole, so we have 32. And then if we add all that up, we get the molecular mass of ethanoic acid, which is 60 grams per mole. So we've found out how much a mole of ethanoic acid weighs, 60 grams. How about the other reactant, sodium hydrogen carbonate? Well, we just do the same thing again. Draw out our table. Sodium 23, hydrogen 1, carbon 12, and 3 oxygens, which is 48. Add all that together, and it comes to 84 grams. Now, it just so happens that these chemicals react in a 1-to-1 ratio. If we were to write out the chemical formula, it looks like this. So we know that 1 mole of vinegar reacts with 1 mole of sodium hydrogen carbonate to give 1 mole of sodium ethanoate and 1 mole of water and 1 mole of carbon dioxide. And it was that carbon dioxide that we were after in order to put out our tea lights. Now, let me introduce you to another guy. This guy is called Avogadro, and he came up with a whole bunch of laws in chemistry, but this is one that we're particularly interested in. It's called the ideal gas law. And basically he said that equal volumes of all gases at the same temperature and pressure have the same number of molecules. In other words, 1 mole of gas occupies 22.4 liters. Well, that's a huge amount. We don't actually need 22 liters of carbon dioxide for this experiment. In fact, I was using a 1 liter measuring jug. So what we're going to do here is we're going to take all of our molecular weights and divide them by 20, because we don't need 22, we need about 1 liter. So if we divide everything by 20, that would get us in and around there. So we look at our sodium hydrogen carbonate, 84 grams per mole. If we divide that by 20, we get 4.2 grams, which is why I asked you to weigh out between 4 and 5 grams. And if we look at our ethanoic acid, which was 60 grams per mole, we divide that by 20, we get 3 grams. Now, it just so happens that the Tesco vinegar that I was using has 5% acidity, which means that it's 5 grams of ethanoic acid in every 100 mils. Well, if it's 5 grams in 100 mils, that's 1 gram in 20, and to get our 3 grams that we needed 60 mils. And what we essentially did was to create a fire extinguisher. This is the principle by which fire extinguishers work. Carbon dioxide is a dense gas, so when you pour it over the flames, it separates the oxygen from the flame, and therefore without oxygen, as we all know, the fire triangle, fire cannot burn, and it puts the flames out. So I hope you enjoyed this science experiment you can do at home. I hope you learned something, and I'll catch you next time.